Alright. What we're going to do in this lesson is talk about properties of atoms, and we're going to try to correlate trends in properties of atoms with their location in the periodic table and with their electron configuration. Alright. First, let's talk about ionization energy. The term first ionization energy refers to the energy that you need to remove one electron from a neutral atom. Okay, that's the minimum energy. Actually, that's the minimum energy that you need to remove an electron from a neutral atom. The second ionization energy is the energy that you need to remove a second electron after you've taken out the first electron. So that would be the third ionization energy. That would be the minimum energy you need to remove a third electron after you've taken out two electrons. Okay, so let's just do a quick check of that concept. What would you call the energy needed for this process? You have a sodium atom in the gas phase, okay, gives you sodium ions and electrons. Okay, so this is an atom losing an electron, so the energy needed for this is the first ionization energy. And if you look at the second one right here, you have sodium with a +1 charge, losing an electron, okay, and giving you sodium with a +2 charge. The energy needed for this to happen is called the second ionization energy. So that's what ionization energy is. All right. Now, unless otherwise specified, when we use the term ionization energy, we generally refer to the first ionization energy. And like I said, that's the minimum energy needed to remove an electron. Now, the energy you need to remove an electron depends on the orbital where the electron that's being occupied by the electron. Okay, so valence electrons are easier to remove than core electrons. So you can think of the first ionization energy then as the energy needed to remove the valence electron from an atom. So here's an example. Sodium is 1s2, 2s2, 2p6, 3s1. That's the electron configuration. That's 11 electrons. So you have 2 electrons in the core, in the 1s orbitals. You have 2 electrons in the 2s orbital. Okay, 2s and 2p. So in the second shell, you're going to have 8 electrons. Okay, you have 2 electrons in the innermost shell, the 1s shell, and then you have that final electron, the outermost electron, much further away. Okay, remember, as you go to higher quantum numbers, you're going to higher shells, you're looking at the average location that's much farther away from the nucleus. So that 1 electron in the 3s orbital would be much farther away from the nucleus. So which electron would be the easiest to remove? That would be the electron in the 3s orbital. Okay, so the energy needed to remove that, and the minimum energy needed to remove that electron is called the first ionization energy of sodium. You can look up values of ionization energy from a variety of sources. You can go to webelements.com. Okay, and let me show you where you can find that. If you go to webelements.com, if you click on sodium, for example, right here, okay, over on the right-hand side, atom properties right here, okay. You have electron shell properties. Okay. Here you have the first ionization energy of sodium is 495.8 kilojoules per mole. Okay. The second ionization energy is 4,562 kilojoules per mole, and you have a graph right here of the first, second, third, fourth, and so on ionization energy for sodium. All right, so let's go back to our lesson. Another place where you can find this is there's some periodic tables that have lots of data on them. This one in particular from the NIST. So you go to physics. You just do a Google search for periodic table and then put site, specify the site as physics.nist.gov. So for example, sodium here, you're given the ionization energy. Down here, you should see a legend on that periodic table that will tell you what the ionization energy is. It's 5.1391 in this particular case, this is given in electron volts. Okay, whereas the one that you find from webelements.com is given to you in kilojoules per mole. So that you have to convert that. If you want to do that on a per atom basis, you'll have to divide that by Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. Okay, so you would have to do 495.8 kilojoules per mole. Okay, divided by, or you can say times 1 mole over 6.02 times 10 to the 23 atoms. So that would give you the number per atom. And so that would give you kilojoules per atom. Okay? And you can just convert kilojoules to electron volts. 1 electron volt, if you recall, is 1.602 times 10 to the negative 19 joules. All right. Okay, so what's the trend in the first ionization energy? If you look at the elements in a periodic table, okay, this is a table of the first ionization energy. This is helium, hydrogen right here. Okay, this is in electron volts. So hydrogen's around somewhere between 10 and 15. That looks like 13 point something, and then around 25 there for helium. So it's increasing, going from left to right in your periodic table. Okay. Lithium, second row elements here, you go from lithium to neon. The general trend you can see is also increasing. So in any given row of your periodic table, okay, the element or the atom with the highest ionization energy is the atom on the far right, the noble gases. Okay, so in any given row, the element that has the highest ionization energy would be the noble gas. Now, if you look at top to bottom, what happens? Within a given group, okay, let's compare, for example, sodium and potassium. Okay, so sodium's right here, potassium's over here, all right, lithium's right here, hydrogen's right here. So within a given row, within a given column, a vertical column, it decreases. Let's look at helium to neon to argon, so decreasing from top to bottom. Okay, so top to bottom, it's decreasing. Left to right, it's increasing. Or another way you can look at it, you can say it's increasing, increasing towards helium, okay? Increasing bottom to top, increasing left to right. So the top right corner of your periodic table, the atoms there would have the highest ionization energy. All right? But note, if you look at closely at this general pattern, you see there are exceptions here and there. So if you go from beryllium to boron, you see a drop. You go from nitrogen to oxygen, there's a slight drop. Okay. Generally, when you're going from group 2A to group 3A, you're seeing a drop there because you're going from a 2s, in this case, to a 2p subshell. So when an electron is in a 2p subshell, it would be a little easier to remove. We'll explain that in a little bit more detail later. Okay, so, and here in the case of nitrogen, you're going from a half-filled subshell, 2p3, and the valence configuration for oxygen would be 2p4. You're going from a half-filled, where your electrons are in separate orbitals, parallel spins, and you're going into oxygen, where you have an extra electron that would have to pair up with one of those unpaired electrons. So that would lead to extra repulsions on the outside among the electrons, would make it a little easier to remove the electron. Remember, ionization energy is a measure of how hard it is to remove an electron. The harder it is, the higher the ionization energy. Okay. Let's look at trends in atomic sizes. Okay, this is a figure that summarizes the trend in atomic sizes. The atomic radii here, so these are given in terms of the radius of the atom. Okay, in picometers. So lithium right here is 152 picometers. So it's group 1A all the way to group 8A over here, the noble gases. What's the trend that you'll notice? Going left to right, it's decreasing signs, right? So left to right. General trend in the first in atomic size. Going left to right would be decreasing. Okay, that's the opposite of the trend in ionization energy. As you go left to right, it gets harder to remove the electron. As you go left to right, the size of the atom shrinks. Top to bottom, okay, you'll notice the trend is increasing. So let's answer this question right here. Arrange the following in order of increasing atomic size: sodium, rubidium, chlorine. What's another way of, what's a quicker way of doing this pattern here? You can say the size would be increasing, decreasing going up, and decreasing going to the right. All right? So that would be the decreasing trend, okay, going up and to the right. So the top right corner of your periodic table would have the smallest sizes. So where is sodium and where is rubidium and chlorine? So here's sodium right here, rubidium's over here, and chlorine is over here. So the trend would be decreasing that way, decreasing upward, decreasing to the right. So in order of increasing atomic size, you'd say chlorine is the smallest, followed by sodium, followed by rubidium. All right. Let's do a quick check. Ionization energy of bromine atoms is the energy associated with which of the following? What did we say ionization energy was? Unless otherwise specified, we mean the first ionization energy. So we're talking about an atom in the gas phase losing an electron. So giving up an electron, what's left behind? That would have to be Br and the +1 charge. So that's this one right here. Bromine going to Br plus electron. Okay, that's the definition of ionization energy. Okay, let's look at this one. Which of the following has the highest ionization energy in the period where it belongs? Remember, a period is a horizontal row. Is it neon, sodium, bromine, or manganese? Okay, what did we say the trend was in ionization energy? It's increasing that way, increasing that way. All right, so you move to the right. Going up to the right, it's increasing ionization energy. All right, but look at this question. It's just saying in the period where it belongs. That means for every period, okay, in period 2, in period 1, row 1, helium has the highest ionization energy. In row number 2, neon has the highest ionization energy. In row number 3, argon has the highest ionization energy. In row number 4, krypton has the highest ionization energy. So the answer to this question is neon. Okay? All right. How do we explain the trend in ionization energy? What you need to do is examine your valence electrons and use Coulomb's law. In general, remember it's the valence electrons that you need to get rid of, that will be lost by the atom when it ionizes, right? And we talk about ionization energy. So the farther that valence electron is from the nucleus, that means the weaker the inward pull on that electron by the nucleus. So it's going to be pulled into the nucleus. The nucleus is positive, the electron's negative, right? It's going to be pulled towards the nucleus. But so if you want to remove it, the farther it is from the nucleus, the easier it is to remove. Remember, Coulomb's law says that the force is inversely proportional to the square of the distance. So if you double the average distance from the nucleus, you're going to quadruple, and you're going to cut the force that's holding it by a fact to a quarter of what it is. Okay. Now the other factor depends that the attraction depends on is the nuclear charge. So the more protons you have in your nucleus, the stronger the pull on those electrons in the valence electron towards the nucleus. Okay. And then the other thing you need to consider is within that valence shell, okay, there's going to be other electrons that's going to partially shield each individual electron from the pull of the nucleus. So there's going to be repulsion from the other electrons. In other words, let's say you have 2 protons in here, and you have 2 electrons out here, okay? Now, each individual electron out here is not going to feel the force of the 2 protons because it's going to feel a repulsion from another electron. So we say each electron in the outer shell will experience what we would call an effective nuclear charge, and that's what you need to examine to explain the trend, okay? So how do you explain the trend going left to right? As you go from left to right, okay, your outermost electron on your periodic table, your outermost electrons will be in the same valence shell. For example, let's just compare lithium versus beryllium. Okay, electron configuration of lithium is 1s2, 2s1. These are the elements in the second row, and your beryllium would be 1s2, 2s1. Okay, 2s2. Sorry, 4 electrons. So this has a core 3 protons in the nucleus, atomic number 3. It has 2 electrons in the core. Okay, and you have that 2s electron, 1 electron in the 2s orbital. So 1 electron out here. Compare that with beryllium, which has 4 protons in the nucleus. It has 2 electrons in the 1s in the core, and then you have 2 electrons out here. Okay? So going from left to right, you're going to have more protons. So you would expect that the inward pull due to the protons will get stronger as you go from left to right. But there will also be more electron repulsion. Here you have an extra electron in the second shell that would repel that other electron. So that counteracts the effect of the 4 protons. Okay? But if you look at the direction of the force, the force due to the nucleus is always directed inward, whereas the force due to the other electron is not always directed inward. Okay, so like if you have an electron here and an electron there, the repulsion would actually tend to push it outward. Okay, but if the other electron happens to be here, it could push it a little inward. So the shielding then due to the other electron is not going to be complete. Right? So we say that the charge of the nucleus is only partially shielded by the other electrons. So 1 additional proton in the nucleus and 1 additional electron in the valence shell simply means there's a net increase in the effective nuclear charge, because that additional proton is not going to be fully shielded by the additional electron. So going left to right, then we can say left to right, you're going to have an increasing effective nuclear charge. And that pretty much determines the trend going from left to right. As you go from left to right, your outermost electron, okay, will be feeling a much stronger force, okay, due to a higher effective nuclear charge pulling it into the nucleus. So if it's going to feel a stronger force towards the nucleus, it's going to be a little harder to remove it from the atom. So the trend from left to right, okay, of increasing ionization energy is due to a stronger effective nuclear charge as you go from left to right. Like I said, there are exceptions here and there. For example, if you're going from beryllium to boron, the electron configuration of boron is 1s2, 2s2, 2p1. Okay, it's actually a little easier to remove the electron from the 2p orbital as in the case of boron. Okay, so the ionization energy actually drops as you go from beryllium to boron. But the general trend from left to right is increasing. I'm sorry, that's a 2s2. How do we explain the trend going from top to bottom? The trend is, explanation is pretty simple. As you go from top to bottom, you're filling in, your outermost electrons will be much farther away as you go down a groove. Okay, so the pull from towards the nucleus is going to be much, much weaker. If you remember, Coulomb's law says that the force is inversely proportional to the square of the distance. So if you double the distance, so if you double the size of the shell, okay, you double the average distance from the nucleus, the force of the nucleus that's pulling in that electron towards the nucleus is going to get cut by to a quarter of what it was in an inner shell, okay, in a shell that's closer to the nucleus. So you're looking at more or less the same effective nuclear charge, but as you move further away, you're going to see a significant drop in the force on the electrons on the outermost shell. So that explains the trend in ionization energy going down a group. So for example, lithium is 1s2, 2s1. Compare that to sodium, 1s2, 2s2, 2p6, 3s1. Okay. This electron in the second shell versus that electron in the third shell, this is going to be much easier to remove. It's going to take less energy to remove that electron. It's farther away from the nucleus than the 2s electron. Okay. How do you explain this trend in size? It's basically the same explanation as the ionization energy trend. Okay, so top to bottom, okay, the size of the valence orbitals increases significantly. Okay, so as you go from top to bottom, you have increasing size. And left to right, as you're going left to right, you have increasing effective nuclear charge Z, and you're going to have increasing ionization energy. Okay, so the outermost shell is more or less the same, so sizes are similar, but it will be dropping because you're going to be pulling in those electrons a little bit more strongly as you go from left to right due to the increasing effective nuclear charge. So increasing ionization energy we associate with decreasing size of the atom. So let's do some clicker questions here. Which of the following has the highest ionization energy? Is it sodium, rubidium, or nitrogen? What's the trend? It's increasing towards the right, right? So it's increasing that way and that way. So it's increasing this way and that way, the general trend. So you say sodium would have the high, nitrogen will have the highest ionization energy of these three. Let's look at this one. Which of the following has the smallest atomic radius? Remember. So you can see the trend, remember, increasing ionization energy, smaller size. So let's compare oxygen, sulfur, and lithium. Okay, going left to right, you're looking at decreasing size. That's increasing ionization energy. And so oxygen is smaller than lithium. Okay, and going top to bottom, that's increasing size. Okay, so decreasing size going that way, so the answer for that will be oxygen would have the smallest size. Increasing trend in ionization energy across a period from left to right is due to what? Left to right, okay, you have more or less the same size shell, but it shrinks a little bit because of increasing effective nuclear charge. The number of electrons in the core will remain the same. You'll have more electrons in the valence shell, more protons in the nucleus, but you'll have a greater increase in the attractions towards the nucleus as opposed to repulsions from the other electrons. The decreasing trend in ionization energy going down a group is primarily due to, that would be increasing size of the valence shell. Okay, so now we're ready to explain ion formation. Earlier in the semester we said that atoms in group 1A are always found in nature when they form ions. The ions that you get from these atoms are always found in nature to have a positive 1 charge. Like for example, sodium ions in nature are always found with a positive 1 charge. Why not +2? Why not +3? Why not -1? Okay. Group 2A, on the other hand, are always found in nature with a +2 charge. If you find ions of group 2A, Like, for example, magnesium, it's always found in nature to have a +2 charge. Similarly, atoms from group 7A, if they form ions in nature, the ones that you find in nature will always have a -1 charge. So, for example, fluorine is always found in nature to have a -1 charge if it becomes an ion, fluoride ion. The answer to this question, we can now explain this. Okay, the answer lies in the fact that behavior of the atoms, properties of the atoms, depend primarily on the valence configuration, and the pattern that we see here is that the the atoms, when they form ions, they have a tendency to achieve a noble gas-like configuration. So there is some kind of stability that's associated with being able to form ions that have a noble gas-like configuration. Okay. Now, why are atoms in the same group? Why do atoms in the same group have the same behavior? Because they have the same valence configuration. So, for example, all group 1A atoms like lithium, sodium, potassium, okay, they have an S1 outermost configuration. Their valence configuration is S1. By losing that one electron, they all gain a noble gas-like configuration. Similarly, group 2A, like magnesium, okay, beryllium, they have a valence configuration of S2, 2 electrons in the outermost shell, and so they have the tendency to lose those 2 electrons and give you an ions with a charge of +2. But why does it stop at 2? And why does sodium stop at 1? Okay, as in group 1A. And group 7A, by gaining 1 electron, okay, they get a noble gas-like configuration of S2P6. But then again, the question is, why does it stop at the noble gas-like configuration? Why not more electrons after that? Let's see. Let's take a look at how we can explain cation formation. And the way to explain this is, once you've removed enough electrons so you're left with a noble gas-like configuration, it becomes extremely hard to remove the next electron. So, for example, sodium has a neon core 3s1. Once you've taken that 1 electron out, okay, so you now have a sodium ion, you have a noble gas-like configuration. The next electron is going to be much, much harder to remove. Similarly for magnesium, okay, after you've taken out the 2 electrons, then the next electron becomes extremely hard to remove. The reason for that is this. You got your sodium right here. Let's say sodium, okay, you got a neon core. So you have your neon core, which is 10 electrons, and then you have that 1 electron on the outside, okay? So removal of that 1 electron from the outside leaves behind the core, where the electrons are much closer to the nucleus and much more strongly attracted to the sodium. So the next electron is going to be extremely hard to remove. Whereas if you have magnesium, for example, okay, if you have magnesium, you have a neon core again, okay, so you have magnesium, you have a nucleus, you have your core here with 10 electrons again, just like neon, right? And then your outer electrons, you have 2 electrons out here. After you take out the first electron, the second electron is still out there. So it's going to be a little harder to remove that second electron, okay, but not that much harder, okay? But once you've taken out that second electron, it becomes extremely hard to remove the third one. Okay, so here's data from webelements.com for beryllium. Here's the first ionization energy of beryllium, the second ionization energy. So between the first and the second, you're going from 899, so that's about 900 kilojoules per mole, to 1757. Okay, so that's about 1800. So it gets twice as hard to remove the second electron. It always gets harder to remove the second electron because it will have less electrons. The remaining electrons will have 1 less electron shielding them from the nucleus. So they'll feel a much stronger pull from the nucleus. It's always going to get harder. But what happens between the second and the third ionization energy? So here you just double the ionization energy between the first and the second. But after you've taken out the second one, look what happens. From about 1800 to 15,000. So 1800 to 15,000, what would that be? Let me see. 15,000 divided by 1800. That's a factor of 8. Okay, it becomes 8 times harder to remove the second electron. Okay, so it becomes 8 times harder. So beryllium, then you'd expect beryllium after it's lost the second electron. Okay, you can see, if you remember, beryllium comes after helium, so it's got a helium core, 2s2. So it has 2 electrons in the core and then those 2 electrons on the outside. After you've removed those 2 electrons from the outside, the next electron is going to be extremely hard to remove. So that explains why atoms tend to acquire a noble gas-like configuration when they form cations. All right, so next let's explain formation of negative ion. How do we explain anion formation? Why does a fluorine atom tend to become an ion with a -1 charge? In fact, fluoride, negatively charged fluorine ions, you only find it in nature with a -1 charge. You can't find fluorine with a -2. This doesn't exist in nature. You don't find fluorine at a +7. Well, if you're going by the tendency to become isoelectronic with a noble gas, okay, fluorine, in order to become isoelectronic with a noble gas, either has to lose 7 electrons, okay, to become isoelectronic with neon. That's going to require too much energy. We've already seen that every time you remove an electron from an atom, it gets harder and harder to take out the next one. But why does it gain electron? In fact, when a fluorine atom gains an electron, it actually releases energy. Okay, so it does gain some stability there. So from 1s2, 2s2, 2p5, okay, your fluorine atom becomes 1s2, 2s2, 2p6. That's your fluoride ion. Okay, that actually releases energy, and the energy released there is called the electron affinity. So we say fluorine has a high electron affinity. Okay, so that is what tends to happen with fluorine when it interacts with other atoms. It has a tendency to acquire an electron instead. F with a -2 charge, okay, is never observed in nature, and the reason for that is, look what happens when you have fluoride, we say has a neon-like configuration, right? 1s2, 2s2, 2p6. If you add one more electron after 2p6, what comes next? 3s1, right? So you have 1s, 2s, 3s, 4s. Remember, this is the 2p, this is the p block on the right. 2p, 3p, 4p, and so on. So after 2p6, you get 3s1. Well, think of it this way. So you have your fluorine atom, fluoride ion with 10 electrons, isoelectronic with neon, right? You add one more electron to that to get F with a -2 charge. That one extra electron is going to be out here in the third shell, okay? And that electron is not likely to stick around. So F with a -2 charge is never found in nature. Okay. Now, a word about electron affinity. Electron affinity is defined as the energy that's released when an atom gains an electron. So we said that fluorine, when it gains an electron, it does release energy. Now, you can think of electron affinity as really the ionization energy for the ion with a -1 charge. Think of it this way. Fluorine gas atom, an atom in the gas phase, plus an electron gives you F minus. The energy associated with that is called, the energy that's released is called the electron affinity. Well, what's the reverse of that process? You have F minus, okay, giving up its electron to give you back the fluorine atom, okay? The energy for this is called the ionization energy of fluoride. So the electron affinity of fluorine is the ionization energy of fluoride. So what would be the trend in electron affinity across a row in your periodic table and down a column? The trend will generally follow those for the ionization energy, because let's take a look at this one. Lithium, the EA of lithium is really the same thing as the ionization energy of lithium with a negative 1 charge, right? And the EA of beryllium is going to be the ionization energy of beryllium with a negative 1 charge. So, in effect then, remember ionization energy increases left to right. We have to stop at the halogens. This time around, it's the halogens that are going to have the highest electron affinity. So electron affinity increases going left to right. Okay. Now there are exceptions. Okay, and exceptions that have completely filled valence subshells will have very low electron affinity. So beryllium, magnesium, calcium, group 2A, S2, okay, because you have a completely filled subshell, because the next electron will go into a higher energy subshell. Those tend to have very low electron affinity. In fact, electron affinities are not really easy to measure, and so they can't be reliably measured for this group because it's very low. Same thing with the noble gases. Okay, they have a very low electron affinity. Let's consider helium. You got 2 electrons on the outermost shell. If you add 1 more electron, okay, it's going to be in a bigger, much bigger shell. That extra electron is going to be so easy to remove. It's not going to stick around. So the electron affinity for helium is going to be very small. So for noble gases, you have very low electron affinity. There's also a unusually low electron affinity. There's a break in the trend for group 5A. Okay, these have a valence configuration of P3, and that's because in a P3 configuration, you have 3 unpaired electrons spread out among the orbitals in the P subshell, and when you have to put the 4th one in, you're going to have more additional repulsions involved, so you're not get as much stability when you put that 4th electron in. Now, there's also, so what about going down a column? The trend going down a column will pretty much just follow ionization energy as well. So going down a column, okay, there's going to be, remember, decreasing ionization energy, right? The electron affinity will also be decreasing electron affinity. Now, there is a break, though, in going from row 2 to row number 3. So that trend really starts from row number 3 on down. So this means that chlorine would have a higher electron affinity than bromine. Okay, so going down, you have decreasing electron affinity. Okay, but there's an exception. Instead of going down from fluorine to chlorine, it's actually going to go up. So chlorine, we say, will have a higher ionization electron affinity than fluorine. And the reason for that has to do with the size of the group 2 the second row elements, the atoms in the second row elements. They're so small that that extra electron is going to be going into a much crowded area as far as electrons are concerned. It's going to experience a much stronger electron repulsion. Okay, so you're not going to have as much of an energy release that you might with the atoms in that row. Okay. Comments about ionic bonding. If you look at look up the ionization energy of sodium, you'll find that it's 5.1 electron volts. In other words, if I were to remove an electron from sodium, that's going to require an input of 5.1 electron volts. On the other hand, if you look up the electron affinity of fluorine, if you attach an electron to fluorine, you're going to get fluoride ion, and the electron affinity is 3.4 volts. So it's going to release 3.4 volts. So the difference between these two is 1.7 electron volts. It takes more energy to remove an electron from a sodium atom than the amount of energy you can release by putting that electron into a fluorine atom. So that's not exactly what we would consider a favorable condition for forming noble gas-like ions. Remember, sodium is a noble gas-like, has a noble gas-like configuration. Fluoride has a noble gas-like configuration. It does actually require energy of 1.7 electron volts. Where does the stability actually come from? It is achieved when the cation and the anion move closer together. If you remember, you can plot potential energy versus the distance between 2 particles. So in the case of 2 ions, typical plot would still look like this. Okay, so this is potential energy versus distance. Distance here is r. Okay, And in fact, if this well depth, we talked about this earlier in the semester, is about 5.3 electron volts. Okay, so when your sodium, oops, this should be fluoride and fluoride. If your sodium and your fluoride ions in the gas phase were to get together, okay, this well depth is 5.3 electron volts. A third body has to come in, okay, and take away 5.3 electron volts. So this is your bond dissociation energy. If you have a sodium fluoride, this should be sodium fluoride, I'm sorry about that. If you have a sodium fluoride molecule in the gas phase, okay, if a pair of sodium and fluoride ions stuck together in the gas phase, not in the solid, in the gas phase, for them to be able to separate, somebody has to come in and give them 5.3 electron volts. Similarly, for these two ions in the gas phase to get stuck, somebody has to take away at least 5.3 electron volts for them to get stuck. Okay, so that's your, and they're not going to get stuck if the third body doesn't come in, because eventually they're going to get so close together, and the charged particles are going to be so crowded, there will be a net repulsion. Okay, and so they'll still separate if the third body doesn't participate in the process. Okay, now, so that's 5 electron volts released by just giving released to a third body when those two ions get together to form a molecule in the gas phase. Okay, like I said, this is fluoride. Okay, and once, in fact, and then from the gas phase, if you go all the way to form solids, if you have these ions get together to form a solid, then it will release even more energy. Okay, as you know, ionic compounds, as they exist in nature, are, under ordinary conditions, are solids. Okay, that will involve an even bigger release of energy. The total energy release in going from ions in the gas phase, sodium and fluoride ions in the gas phase, to sodium fluoride in the solid, okay, would be 9 electron volts for every pair, on average 9.5 electron volts for every pair of ions. This is what's called the lattice energy of the solid. So that involves a tremendous amount of energy release and a lot of stabilization going on there. Now, how do we explain transition metal ion formation? Transition metal cations, as we've learned earlier, typically, most commonly, you'll find those with a charge of +2, although they tend to have other charges. They tend to be found with other charges in nature, +1, for example, or +3, okay, or +4. And the explanation for why +2 is the most common charge you'll find is that the outermost s electrons are the ones that are actually lost first. So in iron, for example, the electron configuration is argon, 4s2, 3d6. Okay? The electrons in the 3d are actually in a lower energy orbital, okay, than the 4s, even though the 4s is filled first when we construct the electron configuration to get the most stable configuration. So it's actually these 4s2 electrons that are removed first, and so that's the explanation why transition metal cations tend to have a charge of +2. Now, if the charge is +3, that simply means, so that means the electron configuration, for example, for iron with a +2 charge is argon core 3d6. Okay, so the 4s2 electrons are gone in iron +2. Now, if you have other charges higher than 2, for example, +3, then the next electron will come from the d orbitals. Okay, so iron with a +3 charge would have an argon core. Instead of 3d6, you're now going to have 3d5. So let's look at some clicker questions here. What is the electron configuration of naturally occurring aluminum ion? Let's see, aluminum's over here. So you would expect, okay, so what's the electron configuration of aluminum? Neon core. After neon, you do 3s2 and then 3p1. It's in the p block, right? This is in p1. So what's the electron configuration of aluminum ion? Well, you would expect it to be isoelectronic with a noble gas. It will be positive. It's a metal. And so it will be isoelectronic with neon. So the answer would be this one here, neon core. Let's look at this question right here. Which atom's first 5 ionization energy best resembles the pattern shown in this graph? Let's look at this graph. There's the first, second, third ionization energy, fourth, and fifth. Well, after the first 3, you can see a drastic jump in the ionization energy, right? So that means there must be 3 electrons in the outermost shell that are relatively easier to remove than the rest of the electrons. So after the 3rd electron, it becomes very hard to get the 4th one. So that means the charge of the ion that you find from this would be +3. So that would be consistent with aluminum. Okay, aluminum, you find it in nature with a charge of +3. After it's lost those 3 electrons, you end up with a neon core, the neon core, from which it will be much harder to remove another electron. Let's take a look at this question. What is the electron configuration of manganese with a +2 charge? All right, so here's manganese. So it's in the D block. So you go D1, D2, D3, D4, and so D5. So you would expect it to have an argon core. After argon, let's see, you got 1s, 2s, 3s, 4s. So the next orbital, the next subshell will be 4s2. After that, it's going to be 3d5. Now this one right here is manganese atom. Okay, the +2 means what? 2 electrons gone, and the first electrons to go whenever you're dealing with transition metals would be the 2 electrons in the outermost s subshell. So this would be manganese with a +2 now. Argon core, 3d5. So the correct answer for this one is D. Now let's compare sizes of atoms versus the cations that you get when an atom loses an electron. Okay. In general, compared to the atom that it came from, a cation would be smaller. It's like if you take off your jacket, you're smaller. Okay? So, and it will have a higher ionization energy. Why? Well, once you've taken out 1 electron, the remaining electrons are going to experience a higher effective nuclear charge. There's fewer electrons to shield them from the nucleus, so each electron is going to feel a much stronger force towards the nucleus. So, which one would have a higher ionization energy? Magnesium. Compare magnesium, magnesium plus, and magnesium plus 2. Ionization energy, first ionization energy would be less than the second ionization energy. That's the ionization energy for Mg plus, right? And it's going to be less than the third ionization energy. So the ionization energy would be highest for magnesium with a +2. And so that would also be the smallest. Think of it this way. Magnesium, you've got right here a neon core. So that's 10 electrons in the core, and you've got those 2 electrons on the outside. Once you've taken out those 2 electrons, okay, you're left with just the core, which is smaller. So Mg with a +2 charge will be the smallest of the 3. Let's compare magnesium +2 versus neon. Okay, magnesium +2 has the same number of electrons as neon, so the electron configuration is 1s2, 2s2, 2p6 for both of them. Which one will have a higher ionization energy? Okay, think of it this way. Magnesium has 12 protons, and it's got, you can think of 2 electrons in the core, okay, and it will have 8 electrons in the outermost shell. Whereas neon will be the same, except that neon is going to have 10 protons instead of 12 protons. So which one will be able to hold on to its electrons more strongly? Magnesium with 12 protons pulling in those 8 electrons versus neon with only 10 protons pulling in those electrons. Everything else is pretty much the same. So magnesium will have a higher ionization energy than neon, although they have the same electron configuration, because your magnesium with a +2 charge has more protons in the nucleus. There's a greater effective nuclear charge pulling in those electrons from the valence shell. Let's compare negative ions versus atoms. Compared to the atom it came from, a negative ion is going to be larger and will have a lower ionization energy. And the reason for that is you're putting more electrons, okay, same number of protons, you're putting more electrons into the outermost shell, so that means extra shielding, okay, so extra repulsions that those electrons out there are going to feel because of that extra additional electrons you're putting in. So extra shielding means extra repulsions among the electrons on the outside, right? So if there's extra repulsions, they're going to spread out more, so your size would be larger. Okay, if they spread out more, they move away, farther away. They're going to be pulled less by the nucleus, and so the ionization energy is going to be lower. It will be easier to remove an electron from out there. Now, if a valence shell is filled, the additional electron will go to the next shell, would be much further away, even easier to remove. So, for example, if you have neon, fluorine, okay, versus fluoride versus F with a -2 charge. Okay. Fluorine would be 1s2, 2s2, 2p5, right? So you got a neon core with 2 electrons, and then 7 electrons on the outside. That's fluorine atom. A fluoride would have an extra electron, so more repulsions is going to spread out. So fluoride would be larger than fluorine in terms of size. And then F with a -2 charge, that second extra electron will come into a much larger shell, because the second shell is going to be filled now, so it's going to be much larger than fluoride ion. And so that's in terms of size. Okay, and in terms of ionization energy, then fluorine would be greater than fluoride. It would be much greater than F2 minus. It's going to be very easy to remove an electron from an F ion with a -2 charge. So easy, in fact, that you don't find it in nature at all. Okay. So how do you compare F with a -2 charge versus sodium? F with a -2 charge, okay, we said has a very low tendency to hold on to its electrons. Remember, we said 9 electrons plus 2, that's 11 electrons. So it's going to be the same as sodium. It's going to have a neon core, 3s1 configuration. But what's the difference? So you got a neon core. Okay, so you have, in the case of fluorine, you have 9 electrons, right? You have 9 electrons right here. And you have 10 electrons in the core, and then you have that 1 extra electron outside. Okay? Compare that to sodium, which has 11 electrons in the nucleus, pulling in that electron from the outside. So 9 versus 11, sodium is going to be able to hold on to its electron more strongly than the F with a -2 charge. Okay, so sodium would have a higher ionization energy compared to F with a -2 charge. And what about size? It would be the opposite, right? So F with a -2 charge, if it were to exist, would be larger than sodium atom. Okay, let's apply those ideas to this question. Which of the following has the largest size? Potassium with a +1 charge, selenium right here, or lithium. Well, let's start off by just comparing this one, and that one. What would that trend be? Size would be decreasing that way and decreasing that way, right? So it's going to be increasing size this way and decreasing size that way. Oops. Okay, so it will be, all right, so it's decreasing that way. If you go the other way, that would be increasing size. So potassium is larger than selenium, it's larger than lithium. So it's not selenium, it's not lithium. Okay? So let's just compare potassium and potassium plus. Potassium is argon core 4s1. That's the electron configuration. And potassium with a +1 charge is just the argon core. So this is going to be smaller. Okay, so this potassium would have to be the largest of these listed here. Which of the following has the highest ionization energy? Let's see. Neon, magnesium with a +2, and then you have magnesium, just plain magnesium, and fluorine. Okay, first of all, going left to right, increasing ionization energy, so you can rule out fluorine, right? So now let's compare magnesium versus magnesium +2. Well, magnesium +2 has already lost 2 electrons. It's going to be very hard. It's going to be very hard to take out another one compared to just magnesium. So it can't be magnesium. Okay, remember, as I go from magnesium, magnesium +1, magnesium +2, and so on. It gets harder and harder to remove the next electron. So let's compare neon then with magnesium +2. Now neon and magnesium +2 are isoelectronic. Magnesium has 12. So magnesium +2 would have 10 electrons. They both have the same electron configuration. 1s2, 2s2, 2p6. But which one will have a higher ionization energy? Magnesium +2 would have a higher ionization energy because it has more protons compared to neon. Okay? So it has more protons pulling in those outer electrons when compared to neon. It has 12, neon has only 10 protons pulling in those outer electrons. So the correct answer is magnesium with a +2 charge. Which of the following has the largest size? Okay. Fluorine versus chlorine, and then fluoride versus chloride. Going down, size increases, so it can't be fluorine, okay? Chlorine versus chloride, the negative ion is larger, right? You're putting an extra electron in the outermost shell, that increases the repulsion among the electrons, they spread out. So chlorine is larger than fluoride. What about fluoride versus chloride? And it's going to be the same argument. Going down the row, the outer electrons here are much further away, so it's not going to be fluoride. Chloride would be the largest. Let's talk now about electronegativity. Electronegativity refers to the ability of an atom to attract shared electrons. Okay, and the trend will generally follow the ionization energy, and the trend stops with fluorine. So fluorine, we say, is the most electronegative atom. Okay, so going left to right, it's increasing electronegativity. And so as you can say, electronegativity is increasing towards fluorine. Now, why do we stop at fluorine? Why do we ignore the noble gases? Because these are atoms that tend not to form covalent bonds. They tend not to share electrons. Okay, so among those atoms that can share electrons, fluorine would be the most electronegative. Pretty much follows the trend in ionization energy and electron affinity. If it's hard to remove an electron, and then that means that suggests you have an atom that has a strong attraction for its electrons. So if it's sharing electrons with another atom, chances are it's going to attract the electrons more than the other atom would. So which of the following has the highest electronegativity? Sodium, bromine, or fluorine? Here's sodium, here's bromine, and fluorine. Well, we just said fluorine has the highest electronegativity, okay, increasing towards fluorine. So the lowest electronegativity would be down here, okay? Rubidium, cesium, francium would have the lowest electronegativity. Which type of element has the lowest electronegativity? Well, if it's increasing towards fluorine, so you have the highest here, where do you find the lowest? Down here, and the lowest would be with the metals. Okay, metals have a very low attractions for their electrons. In fact, that's the reason metals are very good electrical conductors. Okay, the electrons in the metals are so loosely held that you can think of a metal as just a bunch of nuclei that's buried in a sea of electrons.